Welcome. These are the notes for section 3.2, day 1 for college algebra. We are going to start looking at polynomial functions. Our learning objectives today are just to identify what makes something a polynomial function, to recognize the characteristics of graphs of polynomial functions, that they are smooth and continuous, and to determine the end behavior based on the degree and leading coefficients. We will use factoring to find the zeros. We will identify the zeros and their multiplicities, and we will use the intermediate value theorem to determine the existence of real zeros. All right, so first of all, just our definition of a polynomial function. It is a function where the coefficients are real numbers and the exponents are positive whole numbers. All right, so when I look at these examples, it says to circle the ones that are polynomial functions and cross out the ones that are not. So the first thing I look for is, do I have all real coefficients? Okay, those are those front numbers, the numbers in front of our x. So in part A here, I do have real coefficients, the 2, the -3, and the 5. Then I look at the second criteria, that is the exponents have to be positive whole numbers. And right here, I have a -1 as an exponent. So that means this is not a polynomial function. Okay, going to question B. Again, our coefficients are all real numbers and our exponents are all positive whole numbers. So yes, that is a polynomial function. For part C, notice here that we have a variable as a power. That can't be the case if it is a polynomial. So this is not a polynomial function. And for part D, we do have exponents that are all nice positive whole numbers. We look at our coefficients. We have a -0.5, a 1, and a -pi. Pi is a real number, so this would be a polynomial function. Our definition of the degree of a polynomial function is that it's its highest exponent. All right, so you find the highest exponent in the whole thing, that is your degree, and that's going to tell us a lot about the graph. Our leading coefficient is that coefficient, that front number of our highest exponent. Okay, so we look for the x term that has the highest power. That power tells us what its degree is, and the number in front of it is considered the leading coefficient. All right, so our next example says write this polynomial in standard form and state the following. So the first thing is getting it in standard form. That means highest power down to lowest. So I would rewrite this. The -x to the 4th is still my first term, but then notice we have some x squareds. Those would come next. So I have a positive 34x squared. Then I would put my x's down, so positive 15x, and then my constant, -12. Make sure that when you move things around, you take the sign here with it. So that was a -12. We'd want to move that negative along with it. Okay? All right, then they've asked us to determine the degree. The degree, remember, is your highest power. So in this case, we look at our first term here, since we've put it in standard form, highest power down to lowest. Our degree would be 4. The number in front of that term is this -1. Okay, so that would be our leading coefficient. Our constant term is the one that has no variable. Okay, so in our example here, that would be my -12. All right, we are going to look at some basic graphs, and we'll look at the degree of the polynomial and that leading coefficient to kind of help us figure out what these are going to look like. But for now, I'd like you just to pause the video and just on your calculator graph each of these and draw a little sketch. Okay, so go ahead and pause the video, and then when you're ready, turn it back on. All right, for our first one here, y = x squared, hopefully you were able to draw that without even graphing it on your calculator. It is a basic parabola with a vertex at the origin. Okay, our x cubed graph, we've had that cubic twist before. Okay, and if you graphed y = x to the 4th, you'll notice that it looked a lot like y = x squared. It's just a little bit flatter in the middle. Okay, and then y = x to the 5th, again, is a cubic twist, it's just going to be a little flatter as it twists through. Okay? And then looking at our negative versions, that negative in front is just going to flip it upside down. All right? So our x to the second power here with a negative, excuse me, is just going to be an upside down parabola. Our x to the third with a negative is going to cause that twist to flip. Okay? Y to the negative, y equaling negative x to the fourth, again, is an upside down parabola type shape. Again, a little flatter in the middle. And our last one, again, we're just going to flip the graph right above here. Okay? Now, I did kind of color code them. So if you look at all the blue ones, they have similar shapes. Either both arrows are pointing up or both arrows are pointing down. If you look at all the red ones, again, similar shapes, but arrows are pointing in opposite directions. So on one side of your graph, the arrow's pointing down. On the other side, our arrow's pointing up. We are asked to describe end behavior. Now, your textbook uses a more simplified version. We are going to actually change the format that we write this in. So in your book, it will say things like rises on the left, falls on the right, or rises on the left, rises on the right. So your book is going to use rise or fall as its notation. We are going to change that. We are going to write it using limits. So looking at our blue ones, we'll start with our first one here, y equals x squared. The notation says, what is the limit, abbreviated LIM, what is the limit of my function? Okay? And f of x, remember, is just y. So what is the limit of y? Well, in this case, our y values are pointing up on both ends, right? The arrows are pointing up. And if we continue up far enough, we're going to get up to infinity. So we look at two different directions. Okay. The first one says, what happens as x approaches the left side? In other words, way over here on the left is negative infinity. Way over here on the right is positive infinity. So if we go to the left towards negative infinity, where is your arrow pointing? And in this case, we said our arrow is pointing up, so we are headed towards positive infinity. When we go far to the right, so x here is approaching positive infinity, then our graph is still pointing up towards positive infinity. Okay? Now, that notation, that same thing I just wrote, would be the same for this one. Excuse me. Because the arrows are pointing in the same direction. Okay? For our red graphs on the top, we're going to use that same notation. What is the limit of our function? Where are my y's going? I have to write it out twice because I have to look at two different x directions. If we go towards negative infinity for x, so x is approaching negative infinity. In this first picture here, my arrow is pointing down, right? So it's falling on the left. It's going lower and lower and lower. So my y values are going towards negative infinity, towards the bottom. On the right-hand side, as my x's go to the right, towards positive infinity, my y value is pointing up, all right? And high up in the y direction would be positive infinity. Okay? So, for the top row, both blue graphs okay, this works for that one as well. On the top, both red graphs have this version. Okay, because the arrows are really going in the same direction. Well, what happens when we flip everything upside down? All right, we're still going to use that same limit notation. So I'm going to say the limit of my function as x goes far to the left towards negative infinity, and also I'm going to find the limit as x goes towards the far right, towards positive infinity. And for my first picture here, this upside down parabola, my arrows on both ends are pointing down, and far down in the y direction is negative infinity. Okay? So again, this would be the exact same thing I would write for that one. Okay? For the two red graphs, the limit of our function as x goes far to the left and as x goes far to the right. Okay? So going far to the left, the further over here that I move for x, the higher up my y value is, right? Because my arrow's pointing up. So as x goes to the left, my y value is going up towards positive infinity. And as x moves to the right, the farther over here I move, the lower my y value would be. So I'm headed towards negative infinity. And this is the same for that one. Okay, so we can really determine the end behavior simply by looking at the power. If you look at all the red ones, the highest power here was an odd number, a 3 or a 5. If you look at all the blue ones, the highest power was even, a 2, a 4. And so if we graphed an x to the 6th, an x to the 8th, they'd still look like these blue graphs. All right, so our question here says, what will y equaling negative 3x to the 93rd look like, and what is its end behavior? So the first thing I start with is its degree. Our degree here, this 93, is an odd number. Okay, so it's going to look like an x to the 3rd, x to the 5th, x to the 7th, any of those graphs. Okay, so that would be the red ones that I just graphed above here. Since this front number, this leading coefficient, okay, my leading coefficient is negative. If we think about our transformations, that means it's going to flip upside down. It's going to be reflected over the x-axis. So it's going to look like my bottom row of graphs here. Okay? So the answer to y equals negative 3x to the 93rd would be just like this one here. It has a negative leading coefficient and it has an odd degree. Okay? So if we had to sketch it very, very quickly, rough sketch, it's going to start high and twist low. Okay? And so for our end behavior, the limit of our function as x goes towards negative infinity and moves to the far left, my arrow here is pointing up, so I'm going to say I'm going up towards positive infinity. And the limit of my function as x approaches the positive side, the right-hand side, my arrow here is pointing down, so I'm going to be heading towards negative infinity. Okay? So to kind of summarize that, we look at the degree. If the degree is odd, the graph is going to be kind of a squiggle or a twist. We sometimes refer to it as a cubic twist. So it's going to be falling on the left, rising on the right. If the leading coefficient is negative, everything gets reflected over the x-axis. So it's going to be reverse. It's going to rise on the left and fall on the right. So like that, positive 1 would look like that. Okay? If our degree is even, then it's going to look like a parabola shape. Okay? Its end behavior is either going to rise left and right, or it's going to fall left and right. And that totally depends on what kind of leading coefficient you have. All right, so positive, it's going to be like this. It's going to rise on both sides. And negative, it's going to fall on both sides. It's going down. Our book refers to this as the leading coefficient test. Okay? So it says use the leading coefficient test to determine the end behavior of each of these. Again, we don't have to worry about all the other pieces. We are just going to study that leading term. So it is an x to the fourth, so it has an even degree. And then we look at our leading coefficient. Our leading coefficient is positive. So nothing has been reflected. We would think of this as a basic parabola. So I would look at it as if it was a regular opening up type of parabola. So the limit of my function as x approaches negative infinity is positive infinity. On the left, my arrow is pointing up. The limit of my function as x goes towards positive infinity, so as I move to the right, again, my arrow is pointing up, so I'm headed towards positive infinity. Okay? For the next one, it is in factored form, so we really have to kind of think about what would this look like if we multiplied all these pieces together. We don't actually have to do the whole thing, we just have to look at each term and say, what would that highest power be? So I have a negative 8x cubed here. If I were to FOIL this out, x minus 1 squared, I would get an x squared as my highest power term. And then for this last one, I just have an x as my highest variable. And if I multiply all of those together, I'm going to end up with negative 8x to the 3 plus 2 plus 1 would be x to the 6th. That would be my leading term. So again, it has an even power. And it has a negative leading coefficient. So think of an even power would be a parabola shape, and the negative in front would flip it upside down. So we're looking at this basic end behavior. Things in the middle can change, but that's going to be the end. The arrows are still pointing in the right direction. So I would say my limit of f of x, I need to state as x goes towards negative infinity, and also the limit as x goes towards positive infinity, towards the right. Because it's a parabola shape, both arrows are pointing down. Both of my answers here would be negative infinity. Okay, so pause the video for a second and go ahead and try that next one. All right, let's see what you did. Looking at our first term, we have a negative x cubed. So we have an odd degree. We have a negative leading coefficient. Okay, so odd degree, think of going in opposite directions. Our arrows are pointing in opposite directions. Normally an x cubed graph starts low and twists up high, but because this is negative, it's been reflected over the x-axis, and it would start high and twist low. Okay, so again, your book would refer to that as it's rising on the left side, but it's falling on the right side of the graph. Using our limit notation, all right, so for the top one, the limit of f of x as x approaches negative infinity. As I move far to the left, my arrow is pointing up. Up is positive infinity. On the right-hand side, my arrow is pointing down, so I'm headed towards negative infinity. All right, moving on. Our next learning objective was about finding zeros. And as we go through this chapter, we're going to learn a lot of different techniques for finding zeros. Keep in mind that zeros, x-intercepts, roots, solutions, all of those terms refer to the same thing. Basically, we're looking for where our graph crosses the x-axis. We are going to start today just finding all the real zeros. Sometimes there are imaginary zeros, and again, as we continue in the chapter, we will look at those situations. For our first one, trying to factor. Okay, the first thing I would notice, I'm trying to figure out when I get to a 0, but I do have an x that's common to all the terms on the left, so I'm going to factor an x out. That leaves me x squared minus x minus 6. Okay, then I look at that quadratic trinomial piece and say, can I factor it further? Okay, so for this one, I would break up my x squared as x times x, and I look for numbers that multiply to be negative 6 and add up to a negative 1 in the middle. So I would have negative 3, positive 2. And then my zeros are just what makes each of those factors 0. So one option, this front x could just be the 0. For this factor, my x could be a 3. 3 minus 3 would give me a 0. And for this one, x could be negative 2. That would create a 0 there. So I have zeros at 0, 3, and negative 2. All right. Continuing, looking at our next one. Again, we're looking for what makes it 0. We have 4 terms, so we're going to try that grouping technique. That's where we look at the first 2 terms and say, I could pull a 5x squared out of those. What it leaves me with is an x minus 3. Then I look at my second 2 terms and say, I could pull a 3 out of each of those, and I'm left with an x minus 3. Okay? As long as the leftover factor here, the x minus 3 matches, that comes down as one of my factors, just one. And the 2 pieces that I pulled out, the 5x squared and the positive 3, makes the other factor. Okay? And now I have to look at what makes each of those 0. The one on the right here, x being 3 would make that a 0. For this one I wrote in black, we're looking at 5x squared plus 3 being 0. If I go to start solving that, I would bring the 3 to the other side, dividing out the 5. I'm going to end up with x squared being negative 3/5. And our next step would be to square root. But if I square root a negative, I'm going to get an imaginary answer. And they just asked me to find the real zeros. So I'm not going to have any real zeros from that factor. My only 0 would be the 3. All right. For part C, why don't you pause the video and go ahead and try to figure out what would make that 0 by factoring. All right, let's check our work. First step would be to factor an x out. It leaves me 3x squared minus 5x plus 2. And then I would try to factor that trinomial part. The 3x squared I would have to split into 3x and x. I need to get a positive 2 on the end. So I'm looking at 2 and 1, negative 2, negative 1. Since I need a negative 5 in the middle, I need the negative options. To get a negative 5, I could put a negative 2 here and a negative 1 there. Inside gets me negative 2x, outside gets me negative 3, which gets me a total of negative 5. So then my zeros, I could have a 0, and what makes 3x minus 2 0 would be 2/3, and our last one here would be a 1. So those would be the zeros for that last one. All right, I would like you to pause the video again and go ahead and try to factor these. They all are factorable. When you are finished, go ahead and turn it back on. Checking our work. We make our f of x turn into a 0. I can factor an x squared out of both of those. It leaves me x squared minus 4, which is a difference of squares pattern. and would factor into x minus 2 and x plus 2. Okay, now my zeros here would be 0 from the first piece, right, from there, and then 2 and negative 2 from each of my other factors. Okay. For our next one, we can factor by grouping, taking an x squared out of the first piece. I have x plus 2 left, and taking a negative 4 out of the second half of it, I have an x plus 2 left. Regrouping, the pieces I pulled out form one factor. The common factor comes down as my next one. Now notice again the x squared minus 4, we can factor that into x plus 2, x minus 2. And then we have that second factor of x plus 2. So my zeros would be positive and negative 2. And for our last one here, we can actually factor out a negative x squared. That's going to make it a little bit easier on us. We have an x squared minus 4x plus 4 left over. And we're looking for when it equals 0. So again, factoring the x squared minus 4x plus 4, we get x minus 2 times x minus 2. So I have a 0 of 0, and I have zeros of 2. All right? Now, you'll notice that in most of these, we had some repeated things. For example, we had 2 2's here. I don't have to write it twice, but I do have to recognize that it showed up twice. Okay? For this one, same thing. I had 2 zeros at negative 2. Okay? Here, I have 2 zeros at 0. We call that the multiplicity. How often it's showing up does help us figure out something about our graph. So if the 0 is repeated an even number of times, like we had 2 3's or 2 5's, then it's going to look like a quadratic where it crosses the x-axis, or where it touches the x-axis. So it's going to kind of look like a parabola. It's going to touch the x-axis and bounce back off. Okay? We say that is multiplicity 2, or 4, or 6, or 8, an even multiplicity. If it shows up an odd number of times, for example, we might have a 0 at 5, but it shows up in 3 places. Okay? Then it's going to look linear, cubic, x to the 5th, that type of thing. Okay? So it's actually going to cross through the x-axis. And again, the more times that it shows up, the more you can determine the shape of the graph. So if its multiplicity is 1, it's going to just cross like a line, all right, be linear. If its multiplicity is 3, then it would actually kind of have a cubic twist shape to it. Let me try to make that a little clearer. So at my 0 here, I'm going to have a twist happening. Okay, that would be multiplicity 3. So all these little pieces are giving us information about the graph that will help us as we go through this chapter. So find the zeros of this one. Now notice it is factored already for us. And then it says give the multiplicity of each 0 and state what it looks like at that 0. So if I want to figure out what makes this whole thing 0, the negative in 4 isn't, the negative 4 in front isn't going to do anything. It's a constant. I don't have an x there. I can't turn it into 0. But I do have an x here, and if I made that a negative 2, that factor would become 0. And I have an x here. If I made it a positive 5, that would turn it 0. So I have 2 zeros, negative 2 and 5. Their multiplicity is based on how many times that factor appears. So for this first one, it appears twice. It has a power of 2, which means the x plus 2 factor is really in there twice. So negative 2, that 0, we would say has a multiplicity of 2. This one is showing up 3 times. So the 5 has a multiplicity of 3. Okay? And we said if the multiplicity was even, it's going to look kind of like a parabola there. It's going to touch and bounce. All right? So I would say it bounces on the x-axis there, or it looks kind of parabolic. If it is multiplicity 3, it is going to look like a cubic twist. It will cross the x-axis. Okay? And we will be doing more with that again as we go through the chapter. The last little piece is something called an intermediate value theorem. So before we start talking about it, I just want you to evaluate this function for 2 different values. The first one, I want you to find f of negative 3, and the second one, I want you to find f of negative 2. So we're just plugging them in. Okay, putting a negative 2 in. All right, go ahead, grab your calculators, or do it by hand if you want. Get me a value. All right, for our first one, we should be getting a negative 42, and for our second one, a 5. Okay, so f of negative 3 is negative 42, and f of negative 2 is positive 5. Then it says, based on your answers, what has to happen between that negative 3 and the negative 2? Well, if you think about a graph, here's negative 2, here's negative 3, okay? We said at negative 3, we are way down here, right, at negative 42. And when x is negative 2, we are up here at a positive 5. And we have a continuous curve. It's a cubic twist. So that means there's no breaks between here and here. And because we're going from a negative value to a positive value, the intermediate value theorem basically says, well, then you had to have crossed 0. You had to have crossed the x-axis. So based on this, we must have a 0 somewhere between negative 3 and negative 2. So that doesn't really tell me what the 0 is, but it tells me there is one in that position. All right? And our reason is, since our y values change sign. All right? So it doesn't matter if we're going from negative to positive or positive to negative, but either way, we have to cross through 0, or that x-axis. All right, so our last question. Use the intermediate value theorem to show that this polynomial has a real 0 between 2 and 3. So our first step, we need to figure out what f of 2 is and what f of 3 is. Okay, so again, we're just plugging them in. 2 cubed minus 2 times 2 minus 5. And 3 cubed minus 2 times 3 minus 5. All right, 2 cubed is 8. We have 8 minus 4, that's 4. 4 minus 5 would be negative 1. 3 cubed is 27. We're subtracting 6, so we're at 21. We're subtracting 5. We're at 16. So again, we are going between a negative value and a positive value. So y values change sign, which tells me we must have a 0 between 2 and 3. All right, so our assignment for today, you are working on page 360, starting with question 1, going to 39, doing the odds. You must have work to support those answers.